Hi everyone, this is Dr. KGS Shanti, Professor, R.M.K. College of Engineering and Technology. In this video presentation, we are going to study about systems and its classification. The three types of classification what we are going to see in this presentation are causal and non-causal systems, inverse systems and invertibility, time variant and time invariant systems. A system is one which processes the input signals, performs some operation on them and produces the desired output signal. So that is called as a system. Right. Now let us see on the first classification, causal and non-causal system. Right. Now as the name indicates, causal system, it is otherwise called as non-anticipative. Why I'll tell you that it is called as non-anticipative? Because it depends only on present input, past input and past output. It does not depend upon future values and hence it is called as non-anticipative. Right, now when we look into the example, we'll be very clear of what I am conveying. Right, the motion of an automobile is causal because we don't know what is the anticipated future actions of the driver. Right, now let us see a numerical example. Y of t is equal to 3x of t plus x of t minus 1. Okay, right. Now in that case, now let us substitute t is equal to 0. In that case, what you get? Y of 0 is equal to 3x of 0 plus x of 0 minus 1. Now what it becomes? 3x of 0 plus x of minus 1. In the same way, find out y of 1. 3x of 1 plus x of 1 minus 1. So what does it become? Y of 1 is equal to 3x of 1 plus x of 0. Find out for y of minus 1. When you find out for minus 1, y of minus 1 is equal to 3x of minus 1 plus x of minus 2. Now look at the outputs. See here, the output at any time y of 0 depends upon present input. X of 0 is present input and x of minus 1 is past input. In the same way, y of minus 1 depends upon x of minus 1 and x of minus 2. So all the three cases whatever we are seeing, at any instant of time, output depends upon only the present and past inputs, and such a system is going to be called as a causal system or non-anticipative. Right. Let us now look into non-causal system. What do you mean by a non-causal system? It is called as an anticipative system. Why? Because it depends upon the future input values also. Right. In the case of our previous case, in causal system, it depends upon the output at any time depends upon present and past. Whereas non-causal system is one which depends upon future inputs also. Right. Now example. Let us look into the example. Y of t is equal to x of t plus 2 plus x of t minus 1. Right. Now let us substitute the values. Y of 0. Right. Y of 1. Y of minus 1. Right, now look into the case of y of 0. In the case of y of 0, it depends upon x of 2 plus x of minus 1. X of minus 1 is past input but x of 2 is future input. In the same way, y of 1 depends upon x of 3 plus x of 0. Y of minus 1 depends upon x of 1 plus x of 2. Right, now what's the inference here? See here, at any instant of time, output depends upon future values also. The highlighted values in red, x of 2, x of 3, x of 1, all these are future values of input. Right, now let us look into a question. We have to determine whether the given system is causal or not. So find out y of 0, find out y of 1 and find out y of minus 1. Right, now look into the answers. Y of 0 depends upon x of minus 2, x naught and x of minus 1. All are what? Past inputs. Y of 1 depends upon x of minus 1, x of 1 and x of 0. Once again, all past inputs. Y of minus 1 depends upon x of minus 3, x of minus 1 and x of minus 2. So what is the inference you get? The outputs at any instant of time depends upon present and past inputs, and hence the given system is a causal system. Now let us see one more example of causal and non-causal systems. Look into the question. Y of n is equal to x square of n plus 2x of n plus 3. For y of 0, find out the value. For y of 1, find out the value. For y of 2 also find out, y of minus 1 also find out the value. So look at the outputs. Y of 0 depends upon x of 0 and x of 3. Y of 1 depends upon x of 1 and x of 4. Y of minus 1 depends upon x of minus 1 and x of 2, which means that the output at any time depends upon future values also. So which means that the given system is going to be what? Non-causal system. Invertibility and inverse systems. Right. When is a system said to be invertible? Let us look into the diagram. I give x of t to a system. I get y of t as the output. Now when I give y of t as the input to the inverse system, the output of the inverse system should be same as that of the original input, which is nothing but x of t. So when I am going to get back the input once again, then that is going to be called as a invertible system. Now let us look into a numerical example. So x of t, the system, the transfer function is multiplication by 2. So what is y of t? Y of t is equal to 2x of t. Now I give it to a system where the transfer function is multiplying by 1 by 2. So 2x of t is the input. When I multiply by 1 by 2, what happens? 2 and 2 gets cancelled and I get the original input once again. So such a system is going to be called as a invertible system. Example is going to be an encoder, right? And examples of non-invertible systems are nothing but y of n is equal to 0 for any set of input sequence. Say if I have a system with y of n to be 0 all the time. So for whatever be the input sequence, if the output is going to be 0, then it is going to be a non-invertible system. Next, we will look into time variant and time invariant systems. Right. Now, when I say a system as time invariant, if the relationship between the input and output does not change with time, or saying in other words, if a shift in input signal, time shift in input signal x of t minus t naught produces the same time shift in the output signal, right? See here, y of t is equal to transformation on x of t. If a shift in input x of t minus t naught, if I find out the transformation, or if I apply on the transformation on x of t minus t naught, I should get y of t minus t naught, which means that the shift in the input has caused a corresponding shift in the output. So if this condition is satisfied, then we say that a system is going to be a time invariant system. See here. In the same way, in the case of DT system, y of n is nothing but transformation on x of n. So if I give a delay to the input, here I represent it as k. In CT systems, I represent it as t naught. So transformation of x of n minus k is nothing but it gives y of n minus k. So if the input is delayed, then the output is also correspondingly delayed. Then such a system is going to be called as time invariant system or shift invariant system. Right. Now look into what is called as a time variant system or shift variant system. If the condition is not satisfied, that is transformation on x of t minus t naught is nothing but not equal to y of t minus t naught, then such a system is going to be called as time variant system. That is, the delay in the input does not cause a corresponding delay or similar delay in the output. Then in this case it is going to be time variant, right? If in the same way in the case of DT system, if t of x of n minus k is not equal to y of n minus k, then it is time variant system. Right. Now let us look into a diagram for understanding or how to test for time invariance. See here, take x of t, give it to a system, you get y of t. Now delay by t naught, you get y of t minus t naught. Take x of t, delay the input itself by t naught. So what is the output you get? X of t minus t naught. Give it to a system, the output what I get is going to be represented as y of t comma t naught. Right? If these two are same, then it is going to be time invariant system. If these two are different, then it is going to be time variant system. Right. Now let us look the same thing what I told you in the previous slide as a diagram. Here I am going to put it as an algorithm. First one is apply a delay to the input. So x of t minus t naught. Compute the output. Right. The output what you get for a delayed input is going to be represented as y of t comma t naught. The next step. Apply the same delay to the original output. So what you are going to compute? Y of t. After computing y of t, applying the delay, you get y of t minus t naught. Now what is the next step? Compare the results of step 2 and step 3. Actually, if they are going to be the same, then it is time invariant. If not, let us look into one problem for time variant system. Determine whether the following system is time invariant or not. The question is y of t is equal to t into x of t. So what is the first step? Take input, delay the input. So x of t, delay, so the delayed output is going to be x of t minus t naught. Next, compute the output y of t comma t naught for the delayed input. So y of t comma t naught is equal to, so in the question it is t into x of t. So t into x of delayed input, so t minus t naught. Right? So I am repeating, first take the input, delay the input. So x of t minus t naught. Compute the output y of t comma t naught for the delayed input. So what is the function? Y of t is equal to t into x of t. So wherever you have x of t, replace it by x of t minus t naught. Now the third step. Take the output yt, delay it by t naught. So here the equation y of t, wherever you have t, it has to be replaced by t minus t naught. You are delaying t by t naught. See here. So what happens? Y of t minus t naught is equal to, here you have t, so t minus t naught, x of t minus t naught. Now compare these two outputs. When you compare these two outputs, they are not one and the same. Hence the given system is a time variant system. Right, now one more problem for DT system. Right, and before that let us look into the algorithm. Apply a delay to the input. So x of n will become x of n minus k. For this, find out the output, which is represented as y of n comma k. Apply the same delay to the original output. So y of n, when I apply delay, it is going to be y of n minus k. Right? Now y of n comma k and y of n minus k, if they are equal, then it is time invariant. Otherwise, it is time variant. Let us look into one problem for DT system also. So y of n is equal to x of minus n plus 2. So what is the first step? Take the input x of n, delay it by, right? Apply a delay to the input. So what it becomes, the input is x of minus n plus 2. When I apply a delay k, what it becomes? X of minus n minus k plus 2, right? So I am delaying the input by k time units. So x of minus n minus k plus 2. Now compute the output y of n. What is y of n for this delayed input? Y of n comma k is equal to x of minus n minus k plus 2. Your function itself is y of n is equal to x of minus n plus 2. So you get this answer. Right. Next step. What is the next step? Take y of n, delay it by k seconds. So what it is? Y of n minus k is equal to, wherever I have n, it has to be replaced by n minus k. So x of minus of n minus k plus 2. So what I get? X of minus n plus k plus 2. Right here, If these two answers are same, it is time variant. I'm sorry, time invariant. If they are not, then it is time variant. Now look into here, it is x of minus n minus k plus 2. Here it is x of minus n plus k plus 2. So both are not equal, which means that it is time variant. Now let us look into one more problem for checking time variance or time invariance. Y of t is equal to 2 plus x of t. What is the first step? Delay the input. So x of t is going to be delayed by x of t minus t naught. Compute the output. So y1 of t is equal to 2 plus x of t minus t naught. What is the next step? Take y of t, delay it by t naught, right? So y2 of t is equal to y of t minus t naught is equal to 2 plus x of t minus t naught. Now in this case, y1 of t is equal to y2 of t, and hence the given system is a time invariant system. Thank you all students.